Okay, so here we're going to try to show the connection between the electron current and the drift speed and the electric field. So in the previous video, we defined a variety of terms. Electron current is the number of electrons passing through a location divided by the time it takes for them to do that passing. It's the rate at which they pass that location with respect to time. And the number density of the electrons is how many of them are available to move per unit volume. And then the drift velocity is the average speed for those electrons through our conductor. So we get them moving at all when we connect whatever we've got to some source of potential difference, so we can generate an electric field running through the darn thing. And well, what does that look like? So we know we get an electric field that there's going to be a force exerted on these electrons proportional to the field strength, and then divided by, or then multiplied by the charge on the electrons. We recall that the elementary unit of charge is our name for the charge on a proton, or the negative of the charge on an electron. And so when we work with the charge there, instead of writing Q, we'll go ahead and use lowercase e, and we'll talk about the magnitude of the force that's being exerted here. So we want to take a look at our speed of any given electron here along this direction. If this is our x direction here, then the speed of any given electron gets to equal some initial speed plus its acceleration times the change in time, for an acceleration that is constant, or if we're looking at average accelerations. And since we're going to be looking at all these electrons in bulk and looking at stuff like the drift velocity, which is a sort of average velocity for all of these electrons, then looking at averages for acceleration and constant acceleration is valid. And what does that acceleration look like? Well, we recall from Newton's second law that if we have a constant mass, acceleration is our net force per unit mass. So that's the electric field times the charge divided by the mass. So this all gets to get dumped back in here. And we can say, all right, our given speed for some electron in our x direction here is whatever it starts with, plus that charge times the field over m delta t. And here we're looking at, we're sort of looking at magnitudes of this speed. This is going to be like the negative e here for the acceleration. It's going to go the direction opposite the field. Here I'm indicating the field is in the negative x direction to account for that. And so we take a look at this and we want to see, well, all right, drift speed then is going to be the average of all these things. And so it gets to equal Vx average is our drift speed. And that's going to be the average of the original speeds plus the average of all those other business. Well, the electron charge is always the same. Our electric field is uniform. Mass of our electrons remain the same. And so what we're really looking at is our average time for which they're accelerating. What is this average time when they get to accelerate? Well, that's the time when they're not involved in these collisions with the nuclei. I mean, okay, they're always subject to the different electrical forces here, but we can model this as if there's a distinct time where the nuclei have negligible effect, and so they're basically coasting until they bounce off of a thing, like so many pinballs in a pinball machine before it gets to ricochet off of bumpers or what have you. And so this is our average time between all these little nanoscale collisions that are going on in here. And we had to give that its a whole new definition and name, that particular time. So our delta T average, which is our average time between collisions, we're going to give it its own symbol, lowercase tau. And this is T. This is our tau. It's the same tau that we're using for torque, lowercase Greek equivalent of T. So we can just then swap that out there, call that tau. And then our average original velocity, our average velocity here, this is the average speed that these electrons have in the absence of this field. You turn the field off. And we know that, okay, they're bouncing around in here, but that's thermal vibrations. And their speeds may have some non-zero value as they're bouncing around, but their velocities don't. They're not moving in bulk in the absence of an electric field. And so this drops out. And so what remains then is just that our drift velocity then gets to be just this term over here. So I'll go ahead and shove that over here on the left, or on the right again, rather. Yeah, your left, sorry. That our drift velocity in terms of the E field suppose it's more drift speed that we're looking at here, is equal to this fundamental unit of charge times the strength of the field times the time between interactions divided by the mass. In fact, it's useful often to reorganize the arrangement of these letters here and stick the field off here. So we can call it, say that it's in proportion to the field strength. And then, now that we have that, and we have electron current, we can express electron current in terms of the field as well. And so, let's go ahead and do that. So, IE is NE A D is NEA times E tau over M capital E. And then I'm going to stick that over here on the right-hand side as well. And I'll juggle around the, I'll move around some of these quantities in the numerator for convenience for what is to come. So, that is N E tau A N E. Okay. So I'm going to stop here, and then we're going to bring it all home and connect all of this to electric current proper, and get a sneak preview of a relationship that we call Ohm's law, or a version thereof.